those problems, paper problems are trivial, and for the programming assignments, as long as you finish the homework one, you have the decision tree algorithm in your hand, you do some simple modifications to implement your ADA boosting and bagging algorithm. So I think it won't be too hard, and but you need to spend some time debugging your algorithm and run them on the real data set and record results. Right? So I just want to emphasize again, do it early. Allocate some time in weekends and finish everything. And the second thing is about the midterm report for the course project. So you might have noticed we have created an assignment. Right? So the midterm report is due right before the spring break. So so to avoid those kind of homework or midterm reports destroying your spring break, so just do it on time. And in midterm report, you should first you should tell us you have a form of group, or you want to do a single solo project. That's fine. It's full of fun, and you need to define the specific problem you want to solve with machine learning. You need to explain why you think machine learning is an important way or is a potential solution for that. And then you need to collect the data and also do some preliminary study, report some results. That's it. And so for any of you who hasn't started to think about the course project, you should do it right now, immediately. And I'm happy to talk to quite a few students. You have discussed with me about potential projects, and I hear it's really fascinating. So for those who haven't started, just hurry up. Those kind of assignments are not, to be honest, it's not tricky, but they really need you to devote your time on that. Like, you cannot finish the last 2 hours. That's not feasible. But if you do it early, I'm sure it won't be too difficult. So any questions about the course project and homework due? Okay, great. So let us go back to the course content. Right, so in the previous 2 lectures, we introduced the general framework for linear models. And for basically, linear models use a type of linear function, right, to do the prediction. If we do the classification, we just look at the sign of the function, right? If the sign is 1, meaning that the function value is positive, or negative, our prediction is simply 1. Otherwise, the prediction is -1. And if we do the regression, we directly use the function value as our prediction. It's called linear regression. In the last lecture, we discussed the first learning algorithm for linear regression. It's called least mean square method. And then from today, we'll introduce several typical and classical learning algorithms for linear classifier. So we'll start with the perceptron algorithm, the most classical one. And it serves as the foundation of the advanced linear classifiers, or large margin classifiers, as we'll discuss later, and also serves the foundation of the artificial neural nets. So in a long time, multi-layer neural networks are also called multi-layer perceptrons. So now we see perceptrons here. So here's the outline. So for perception, we'll first introduce the algorithm of perception. After that, everyone should be able to implement a perception algorithm. And then we'll introduce a bit of theoretical results about perception. called mistake bound theorem. So you will say, in what kind of cases perception can always guarantee to converge, and in what cases, in what kind of solutions perception does not converge. And under convergence, how many number of mistakes it will make during the training procedure. So UC perception is essentially a mistake-driven learning algorithm, or in other words, it's kind of a lazy learning algorithm. Only when it makes a mistake, it predicts the training example is obvious. If it correctly predicts one training example, it does nothing. Then an interesting problem is that how many mistakes the perception algorithm at most make during the learning procedure. And then finally, we'll introduce practically what kind of perception algorithm we will implement. That refers to variants of perception algorithm. And those variants can further improve the robustness of the perception learning procedure and also potentially improve the generalization performance. So this is the basic topic we're going to cover, right? So first, let us look at the perception algorithm. So before that, we need to first review the definition of linear classifier. So in general, we assume our input are n-dimensional vectors, x, and the output is a binary label. And for convenience, we assume each label is either -1 or 1. And linear classifiers are also referred to as linear threshold units in the literature of artificial neural nets. So it classifies an arbitrary example x using the following rule. Right? The rule is as follows. We first compute a linear function, which is the inner product between the weight vector and the input vector, plus a bias parameter. And then we look at the sign of this function. Right? So if the function is less than 0, then we predict y to be 1, right? Otherwise, we predict y to be -1. So the linear classifier of linear threshold unit can also be represented graphically. So it looks like this. It resembles the architectures in like artificial neural nets. So in the very bottom one, on the bottom are the input features. So here we have 8 features and one constant 1, right? And then all those bottom nodes are connected to an intermediate operation node. And on the edge are the weights and bias parameters. So you can see that each edge has a weight corresponds to the feature. So it means that we simply multiply the value at each bottom node with the corresponding weight on the edge and send them to the intermediate node. And then there is a associated operation on this intermediate node. So sigma just represents the summation. That means, okay, just sum up all the input messages. That means, okay, we simply do the summation over W1, X1, W2, X2, until W8, X8 plus B, right? And then the output of this intermediate node will be sent to the sign function. So the output will be the sign function. So you can say, actually, the whole classification procedure is represented the computation message passing through this graph from bottom to up, right? So this is a typical way to represent artificial neural nets. So later, when we introduce artificial neural nets, you will see many such kind of figures. It simply represents how we transform the feature values through linear operations or nonlinear operations, and then transmit those values layer by layer. And finally, you get output as your prediction results. Either the prediction is either like binary, discrete, or continuous. And then we know that linear classifiers have a nice geometry interpretation. Right? So suppose these are the positive examples, these are negative examples. We're only discussing the two-dimensional case, so that corresponds to a plane, right? And then the equality that the classification function p0 in this two-dimensional space represents a line, right? This line actually separates positive examples from negative examples. And this line also defines what portion of the points in the whole plane to be classified as positive examples. Right? So we can say all the points on this side are classified as positive. Why? Because the classification function here, evaluated on any point here, are positive, are negative, right? And all the points on this side are classified as negative because the classification function here is negative. So this line is also called the classification boundary. And we can extend two-dimensional case to like arbitrary dimensional case. Right? In a higher dimensional case, this classification boundary is called hyperplane, classification hyperplane. Right? The hyperplane separates the whole like n-dimensional space into two half spaces. Right? One half space contains all the positive, all the data points predicted as positive, right? And the other half space contains all the points predicted as negative. And an important geometry property is that the weight vector is always orthogonal to the classification boundary or the hyperplane. And you can verify offline. It's straightforward. And for linear classifiers, we only care about the sign, not the magnitude. That means you can multiply the weights W1, W2, and mass parameter B by any positive constant. Then the corresponding classifier is totally equivalent. The reason is that it doesn't affect prediction results. So those are the geometry interpretation of linear classifiers. We'll keep using that to illustrate different learning algorithms for linear classifiers. So I hope you guys are familiar with those videos. So then let us talk about perception. Perception is a way to learn the weights and mass parameters from the training data. So here is this gossip of this history. So the perception paper was first published on a psychology journal. So it's interesting. So actually, in the early development of machine learning and artificial intelligence, psychology and biology has close connections to artificial intelligence. So this was proposed by Rosenblatt. He's the pioneer of artificial intelligence. And when the perception was first proposed, right, there are many hypes and fears that artificial intelligence will like rule the earth and will kill people or whatever. Right? So these are just one example article in the New Yorker. It's very similar to our current situation about artificial intelligence. There's so many hypes. People fear about artificial intelligence not only about jobs but also like kill people. Right? How about what can we do if artificial intelligence can think like human beings, right? As a researcher, as a serious researcher, I can tell you artificial intelligence, although has made amazing progress, is still far from intelligence. So a summary of the perception. Developed, proposed very early, like 1985. The goal of perception is not to be artificial intelligence. It's simply to find a separating hyperplane from a data set. The data set only contains like positive examples and negative examples. The goal of the perception is just to find a hyperplane to well separate positive examples from negative examples. In other words, it's just a linear classifier. And it's interesting in that perception is an online process. In other words, it processes training examples one by one. This is kind of similar to the stochastic gradient descent we discussed in the least square method, but the mechanism is a bit different. And later we'll see actually they can be unified in the same framework. And in practice, there are many variants for perception, and we'll discuss toward the end of this topic. So here's the perception algorithm. So our input, again, is a sequence of training examples, x1, y1, x2, y2, say, to xn, yn. And we assume every input example is represented by an n-dimensional input vector. But here, all the input vector is augmented with the constant 1. Meaning that our classification function is simply the inner product between the weight vector and the augmented weight vector. Right? So this is a notation simplification. That's just for convenience. Any question at this point? So remember, for the sometimes when we want to simplify the representation of linear classifier, we just augment the input vector by constant feature 1, right? And then we fold the bus parameter into the weight vector. Then our classification function is simply the inner product between the weight vector and the bus parameter. So keep this in mind, right? And then perception first initialize the weight vector to be 0. Remember, this initialization is 0. It's not random. It's just 0. And then we sequentially go through each training example. Say, currently, our training example is xi, yi, right? And then we use the current weight vector, say wt, right? Meaning that we process in the t iteration at our current weight vector to give the prediction. So because of the notation simplification trick, so we simply take the sign of the inner product between wt and xt, right? And this is our prediction. And then we compare our prediction with the ground truth for I. If our prediction is correct, then we do nothing. We jump to the next example. If our prediction is wrong, meaning that yi is not equal to y prime, our prediction, then we'll update wt in this way. We'll add wt with add wt to the production between the ground truth label yi and the input vector xi, and then multiply with a positive constant r. So r is also referred to as learning rate. So it takes the same function as learning rate in stochastic gradient descent. And then we jump to the next example. So we just repeatedly go through each training example until convergence or the maximum number of iterations have achieved. That's the perception order. And after the iterations are finished, we return the final feedback. So any questions in understanding this procedure?
Why is it that the yi gives you or tends to give you a better weight vector?
You mean
when you update with your WT
why we conduct such kind of update.
Yeah, what's the significance of y axis? What is it? It doesn't seem like it's a gradient.
Yeah, that's a very good question, and we'll explain it later. Of course, we need to know why we should perform this kind of updates. Why it is useful, right? But here, I just want to ensure that everyone feels comfortable about the whole algorithm procedure, right? It's straightforward, and giving you this pseudocode, everybody should feel comfortable to implement one, right? Any questions? Okay, so let us continue, right? So here, just some reminder, right? So our prediction is why our prediction is simply the sign of inner product between W and X because we use the location simplification tree. We augment X, each X1, X2 to like Xm with a constant feature 1, and correspondingly, we fold the bias parameter B into W to form the new weight vector. I just want to emphasize again and again to avoid you from being like confused. Right? And in practice, right? In practice, you might you might have to deal with data where the labels are 0, 1 rather than -1, 1. In such kind of cases, how can you adapt them into this sampling algorithm? What kind of linear transform? Yeah, yeah. So you can either like replace all zeros by -1, right? That's a pre-processing step. Or you can like you do not need to do any pre-processing, just replace yi by like 2yi minus 1. Why? Why? Anybody can help me? When yi is either 0 or 1, I can simply modify this perception algorithm by replacing yi here by 2yi minus 1. Why?
It'll be the 1 to state 1, go to minus 1.
Yes.
One.
Yes, exactly. Right. This is it's very commonly used trick. So I hope everybody.
So I'm looking at this. It looks like the order of your data will affect the algorithm. Is that true?
Yes, of course. But in general, when the data is linearly separable, you always find out the separable plane, but that's not guaranteed that you will end up with exactly the same. We'll discuss later. That's in regards to the theoretical guarantees about perception algorithm. So back to the point we just made, right? So that 2yi minus 1 trick not only applies to like perceptions, actually many linear classifier algorithm design, and if by default you assume it's -1, 1, you can always replace yi by 2i minus 1 if you have to deal with 0, 1 case. This is just a practical trick. I hope everybody knows that. So one particularly interesting point about perception is that its updating rule is like this, right? So to look into the rationality of this updating rule, right? We can first consider two situations where we make mistakes. Right? So first, if we make a mistake in predicting a positive example, then what is the updating rule? If the ground state label is 1, right? Meaning that we're doing the prediction on positive example. So yi will be 1, right? Then our updating rule is this one, right? Wt plus xi multiplied with this learning rate r, right? And if we make a mistake on that example, then what is the updating rule? minus, right? Because yi is now -1. So later we'll say why when we update the weight vector in this way is good, can improve our model. And here, R is learned rate, is a small positive number, and in practice we usually choose R to be less than 1. But when the data is linear separable, you can choose R to be 1. That's no problem. There's no problem with that. So from the whole algorithm, we can see that the weights, the whole model parameters are updated only when we make mistakes. Right? If there are no mistakes in prediction, we do nothing. We just keep the current model. So this type of algorithm is called a mistake-driven learning algorithm. And of course, this is the simplest version of perception. This is the original version of perception. And to improve the robustness of the perception algorithm, we'll see more. We'll see some errors like voltage perception, like large margin perception algorithm. So remember, if we use the linear classifier, the mistake can also be written as this implicit, right? That is the production between yi and our prediction is no bigger than 0. Why? Anybody can anybody recall this? Why? For a mistake we always have this implicit.
The probability signs, if they're incorrect, so it'll always be negative if they're incorrect, and positive if they're.
Yeah, we can see it by just looking at two different cases, right? So if yi is 1 and we make a wrong prediction, then this inner product must be negative. The production must be negative, right? And yi is -1. If we make a wrong prediction, then our inner product must be positive. So their product must be less than or equal to 0 as well, right? So in other words, we can further state the algorithm step by just using one statement, right? We can simply write if this implicit holds, we just update the weight vector this way. Any questions so far? So everybody feels good? Okay. Yeah. So now let us look at the rationalities of the updated rule, right? So why we should update the weight vector this way? To illustrate, again, we just discussed case by case, right? So first we assume we made a mistake on a positive example. That means the ground truth label y will be 1, right? And our prediction, the linear product between the current weight vector, wt, and the input vector x, will be less than 0. And then, according to our updating rule, right, when we make mistake on positive, we add the current weight vector by r multiplying with current input vector to update the weight vector to wt plus 1, right? Meaning the weight vector in t plus 1's iteration. Right? And here we choose r to be 1 for simplicity. Right? And then to check whether after the updates our model got improved, we want to use this updated weight vector to predict the example again. Then we simply calculate the inner product again, right? So what is the inner product between wt plus 1 and x? Because wt plus 1 is actually wt plus x, right? So just replace wt plus 1 by the summation and do the inner product with x. We multiply x inside. We got the new inner product is a summation of two terms. The first term is inner product between wt and x and plus x transpose x. So here are questions. What's what about the value of x transpose x? What? It's actually square norm of x. What's the property of the square norm of x? It's positive, right? As long as you don't have a full zero input vectors. Actually, it's not possible because we have already done a feature augmentation, right? There must be a constant feature 1 inside the feature vector. And then x transpose x is must positive. With that being said, after the update, the classification function value as compared with the classification function value in the previous iteration, it gets increased. What does it mean for this increase? Or what does it imply?
You're getting closer to outputting 1, which is like 1 and 2.
Yeah, exactly, right? Anyone wants to give us to supplement? So we can look back the case we made a mistake, right? We make wrong prediction on this particular positive example. Why do we make this wrong prediction? Because our classification function value is too small, such that it is below 0. Right? If our prediction is correct, the classification function value should be above 0. So now, if I want to improve the classifier in predicting this particular example x, of course we want to increase the classification function value. Right? And then that is exactly what we have seen here. So we can see that after the update, our classification function value does increase. So although there's no guarantee that when we add a positive constant, the classification function value will end up with being bigger than 0, right? There's no guarantee. If your previous classification function value is too small, like minus 100, you add a constant like 10, you end up with minus 90 is still below 0, meaning that you still make wrong prediction. But at least we improve our model toward the right direction, right? That's the rationality behind the updates. Any questions? And then you can apply the similar reasoning for the negative examples. If you make a wrong prediction on a negative example, that means y is minus 1, then the inner product is bigger than 0, meaning that your classification function value is too large, such that it is above 0. Right? And you will see that after the update, your classification function value will get decreased. So, in other words, in a negative example case, your update also improve your classifier in the right direction. That's the rationality of this exception rules updating. Any questions? Okay, great. So now let us look at it more like in detail from a geometry view to give you a better impression, right? So suppose this is our current data vector. So this is a classification hyperplane, right? Classification boundary, and remember the weight is always perpendicular to the classification boundary, right? And now we have a training example x here. Its true label is positive 1. So will this example be correctly classified by our current classifier? Why? What? Yes. The reason is that only the points on this side, because the points will have the same, have the consistent direction with vector here, they will be classified as positive example because inner product will be positive, right? And all the points on the other side will have the inner product being less than 0, so it will be predicted as negative example. So obviously we make a mistake on the positive example, right? So now let us look at how the perceptron update rule will change the direction of the classifier, right? The classification boundary. So according to the rule, we make a mistake on positive examples. We add our current weight vector by the input vector x. Right? Here we choose constant 1 as the learning weight r. Right? So we use w plus, we update w by adding x. Right? So here is the weight vector of current w, here is x. Right? How can we do the vector addition? How can we do that vector addition?
You basically just plot vector x, tail of vector x onto the point of the w vector.
Yes, yes. We just draw a parallel line, right? So we just move x parallelly such that its starting point coincides with the ending point of w, right? And then we just connect the starting point of w with the ending point of x. We get the addition, right? Vector addition. So this is updated weight vector. And then according to the updated weight vector, we can draw the new classification boundary. This is the updated weight vector. And again, because it is perpendicular to the classification boundary, so the new classification boundary should be here, right? So now, what is the prediction for the x? What's the prediction for the x?
Predict positive this time.
Why? Yeah. Why? Because you can say now all the points on this side, they are consistent with the direction of W nu. So unit product must be positive. So now x state is this side. That means our prediction is positive, right? And all the points on this side are predicted as negative. So see how this update rule improve our model to remedy this mistake, right? Any questions? Yeah, I'm so happy to see everybody looks comfortable, right? Okay, so let us look at the another example when we make a mistake on negative examples, right? So suppose this is our current weight vector and this classification boundary, right? So remember, now the weight vector, direction of weight vector is along this way. So the points on this side will be classified as positive examples. On the other side, classified as negative example. So now we have a negative example on this side. That means we'll make wrong prediction on x, right? We predict x as positive. And now let's see how the perceptron updates rule works, right? So in a negative case, we update w by subtracting x, subtracting w with x, right? And how can we do the vector subtraction? So this is the x and this is our current weight vector. How can we subtract two vectors? Okay?
Kind of the same thing before. You just take your weight vector and bring it up parallel, like have the heads kind of touch. So you have w minus.
Yeah. So subtraction is equal to addition to the minus vector, right? So you need to first reverse the direction of x, right? You get minus x, and then you move the reverse the minus x, right? Which has the reverse direction in parallel, right? Or the same way as in addition, right? You make the starting point of minus x coincides with the ending point of w, right? And you just connect the starting point of w and the ending point of minus x to get the subtraction, right? So this will end up with our updated weight vector. And this is our new classification boundary, which is again orthogonal to the new weight vector. So now what is the prediction for this x? Negative, right? Because now the direction of x is inconsistent with w, right? All the points on this on the left hand side is it will be classified as negative. Okay, so those are basically perception algorithm. I believe it's pretty straightforward, right? So you need to know the algorithm details. The key detail is the updating rule, and you need to know why these updates can really improve the model, right? And of course, perception is not kind of powerful. It's not kind of God, right? You can learn all kind of functions. It only applies to linear functions. That means it cannot learn what it cannot represent. Right? So typically, some parity functions we mentioned in previous lectures, those kind of functions cannot be equivalently represented by linear classifiers. So perception cannot learn classifiers for those kind of functions. So in 1969, Minsky and Papert, they are the big name in the early stage of artificial intelligence. They wrote a very influential book demonstrating that perceptions has a severe limitation in representation power, in that it cannot learn parity function. So they gave the very famous example that is the XOR function. So we are discussing why in previous lecture, right? In homework 2, you are also asked, well, we already know that XOR is not linearly separable, but I also discussed there's some trick to do the feature transformation. Right? If we can augment feature with some smart transformations, we can map the training examples in the higher dimensional space. In this higher dimensional space, then there could be some hyperplane which will separate those examples. Right? So in homework 2, you are asked to invent such a transformation. So these are all about perception. So you need to know that algorithm details. You need to know the geometry interpretation of those updates, and also you need to know its limitation. So, okay, up to now, any questions?
So you just showed us perceptron on a two-dimensional problem. What happens when you go above 3? It seems like it becomes really hard to visualize, but does the perceptron still work well?
Yeah, work well. So those arguments apply in whatever dimensions, whatever feature space. And why? Because we give the analytical analysis, right? We show that for this particular case, right? No matter how many dimensions x have, right? So after the update, if you make wrong prediction on positive examples, the classification function value is always increased. Right? So it's a way to improve the model, right? To remedy the mistake. So that applies to arbitrary dimensions. But for visualization, I mean, for a good geometry interpretation, two-dimensional space is more than enough, right? Of course, you can imagine like three-dimensional space. You can think of like a plane, a hyperplane, right? And really a plane how how to adjust their positions, right? But it's harder to show it. Any other questions?
Sorry, one more. So it almost seems like perceptron can overcorrect. Is that an issue?
What do you mean by overcorrect?
So if you go forward just a couple more, or sorry, yeah.
This one?
Yeah, keep going. So it's like once you get to that set, that correction is pretty dramatic.
Yeah, you're right. You're right. So that's why you can adjust the learning rate R here. So here we simply like choose R being 1, right? It's for illustration, but for practice, like you can choose R actually, as long as positive. It cannot be negative. Negative is wrong.
So if you had some noisy data in there, do you just go until you reach a certain threshold? Is that how you handle that, or?
Yeah, that's a good question. That means, right, if your data is corrupted by some noises, and then the data is not linearly separable, and we're going to discuss immediately. In that kind of case, perception will never converge. Then how can we deal with that? Right? But regarding the algorithm details themselves, and also the explanation of why perception works, is everybody feel comfortable? Okay. So now let us give some theoretical guarantees about perception algorithm. Those theoretical guarantees can characterize perception in a more rigorous way, and say what is the limitation of perception, what is the power of perception, right? So basically, it's called perception mystic bound theory. So the first theorem is called convergence theorem. Convergence theorem tells us that if there exists a set of weights that are consistent with the data, that means the data is linearly separable, then the perception algorithm will guarantee to be converged. It will guarantee to converge. So in whatever orders of data you feed to the perception algorithm, it will always converge. That's a nice property, right? But there's no free lunch. If the training data is not linearly separable, right, as you just mentioned, if data is corrupted, and then you cannot find a linear classifier that perfectly predict all the training examples, then perception will never converge. So it will eventually enter into an infinite loop that it just goes through a set of distinct vectors. It's like I'll have like 10 distinct vectors, W1, W2, W10. So I just update W1 to W2, W2 to W3, until W9 to W10, and then W2 to W1. And do this loop again and again. It will never stop. By practice, that reminds me, even it does not converge, I can force the algorithm to quit, right? I set up a maximum number of iterations, and if it exists, the maximum number of iterations are just stop. But here's the practice. You should be aware. Right? So when the data is good, right, when it's perfectly linearly separable, then it always converges. Don't need to worry about it. But the data is not linearly separable. It's just entered into this cycle. So to introduce the theory of mystic bound, we need to first explain an important concept called margin. And we'll use this margin. We use the concept margin many times, right? So what is margin? We first define margin as the property of hyperplane for a data set. So if the data can be linearly separable by this hyperplane, meaning that this hyperplane can well separate all the positive examples from all the negative examples in this data set, we'll say this hyperplane has a margin. And the margin is the minimum distance between the points in the data set and this hyperplane. So that's the definition of margin. given this example, the margin is simply the distance between this particular positive example and the hyperplane. Why? Because the distance between this point and hyperplane is the smallest as compared with all the other points, right? But here you should keep in mind, we only talk about margin when the data set is linearly separable by this particular hyperplane. If this particular hyperplane does not separate the data, then there is no margin. This is a starting point on this. Any questions on the definition? Okay, so given the definition of margin for a particular hyperplane, right, we can further generalize the definition to the margin of a data set. So now, the margin for a data set is not with respect to a particular hyperplane. So the margin of the data set is actually the maximum margin possible for that data set using any effect. In other words, for this particular data set, right, to compute the margin for the whole data set, we just enumerate all possible hyperplanes which can well separate the positive examples from negative examples. And for each specific hyperplane, we have a margin, right? And then we just pick the minimum of those margins and use this minimum margin as the margin of the whole data set. So for this particular data set, we can say, okay, for this particular hyperplane, we have a margin, right, like this, and it's not minimum, it's maximum. And for this particular, for this hyperplane, it can separate positive examples from negative examples as well, right? It has a margin. We just enumerate all possible separating hyperplanes, compute their margins, and pick up the maximum. And this is called margin for a data set. So again, the margin for a data set exists only when this data set is linearly separable. If the data set is not linearly separable, there's no margin. Any questions regarding the definition?
So why don't, sorry if I'm not understanding this correctly, but I understand the margin of the data set between the enumeration or the summation of both the negative and the positive until it separates it. Why not, like the margin, you just take the margin of the closest positive and the margin of the closest negative?
Well, you can do that. And I doubt in some computational learning theory, there might be some definition as you suggested. But here we introduce margin like this, is simply because it is enough. And later we'll say, but here I just want to throw a question for you, right? So through the definition of the margin for a data set, right? So what can the margin for a data set imply or represent?
If you have a smaller margin, it means they're harder to separate. Whether the data, they're going to be labels are more polarized.
Yeah, exactly. Very good point. That's the motivation to introduce the concept of margin. So the
This is a different question of margin, but we talked about linear classifiers accepting noise, how much noise they can accept. It's not in this lecture, but about linear classifiers. So I was just wondering how that works with perceptron. And if you do have some noise where there's nothing perfectly linear separable, you can just say that it has a negative margin or that it has no margin.
Has no margin.
No margin.
Has no margin.
So how does the perceptron handle something like that? Does it just get to a point where it can't update its weights anymore?
Yeah, as we just mentioned, right, it will enter it will enter into an infinite loop, right? So you can just set up the maximum number of iterations and just quit. But later I will discuss some variants like voltage perception. You can aggregate all the results in all the iterations together to improve robustness. That's the practical trick. But here, I can tell you the margin, yeah. It is kind of indicator of just kind of measurement of the property of the data. So you can imagine the further away all the positive examples from negative examples, the larger the margin, right? And then that means the easier it can be classified with a linear classifier, right? But on the contrary, on the other side, the smaller the margin, meaning that the closer the positive examples and the negative examples, it is harder to find a set really happen, right? So it's kind of measurement of the easiness to classify a particular data set. And it is important. It's very good. It's an important measure or important indicator for the data set, and this we'll discuss it later. We'll discuss later how to utilize margin to construct more powerful classifiers and with better generalization performance. Okay. So here just a review, right? So for general hyperplane, which is represented by the equality where the inner product between a weight vector and x plus bus parameter is 0, and for an arbitrary point, the distance between x0 and h is like this. So as an exercise, you can try to derive this. It's just the absolute value of the classification function evaluated at x0 divided by the norm of the big vector w. And in our perception case, because we use the notation simplification trick, right? So we augment features with 1 and fold the bus parameter into weight. So our classification hyperplane is just the inner product in 0, right? And then apply this formula again, we get the distance between an arbitrary input in the augmented feature space and h is like this. The inner product, absolute value of inner product over the norm of the weight vector. And we mentioned before, right, because we only care about the sign of the function value, right? So if we skew the whole weight vector by a constant factor, positive constant factor doesn't affect the classification, right? So if we choose the weight vector w to be a unit vector, we can just omit the denominator, right? And further, if this weight vector can correctly predict the example x0, then this absolute value can simply be represented as y0 times the inner product, right? Because if we do the correct prediction, this term is always negative. Any questions?
What's the H?
H is the hyperplane. Is this?
Oh,
Yeah. It's just the denote. It just denotes the hyperplane.
oh.
Yeah. This just represents, okay, for an arbitrary point x0, what's the distance? How far away from x0 to h? Any questions? Okay. Yeah. So all those are the preliminaries for looking into this mystic bound theorem. So here, let us look at the details of this theorem. So mystic bound theorem assume that we satisfy two conditions. First, suppose this is our training examples, M training examples, right? And for any feature vector xi, the length of the feature vector is upper bounded by a constant r. This is norm. Norm is length, right? And then suppose there exists a unit vector u. So that unit vector means that the norm is 1, right? Such that there exists some gamma, which is positive, And for any training example, xi, yi, we have this term yi multiplied with inner product between u and xi is no less than gamma. So the second condition. Suppose our data set satisfies the two conditions, then perception algorithm will guarantee to converge. And during the training procedure, it will make at most r over gamma squared mistakes during the training. That's the whole theory. So now let's look into the this theory, right? First, by default, we assume all the input vectors are augmented with constant 1, and that means the weight vector is augmented, has the bus parameter folded into. Right? And second, what does this mean, right? What does the norm of xi less than or equal to r mean? It just means a wall, right? So imagine for an n-dimensional vector, right? So if the norm for all the input vectors is less than or equal to r, you can imagine there's a ball with radius r, right? It contains all the input vectors inside the ball. That's the meaning for this. Right? To choose such r is simple. You just choose you just pick up the input vector whose norm is the largest. You use that as r. And what does the second condition mean? This is very important. What does that mean? So let us read the second condition again, right? So assume that there exists a unit vector u such that for some gamma, for some positive gamma, we have for arbitrary input example xi yi times u transpose xi is bigger than or equal to gamma. So what does gamma represent?
I guess here the accuracy it's because if yi is always positive, it means that you gave you a proper something or proper algorithm.
Yeah. Yeah. First point, very important. Yeah. That means this whole data set is linearly separable, right? And it can be correctly classified with the weight vector u, right? And second, what does gamma mean?
Margin of the data set.
Yeah. Why?
So like you're adding time to your line, it looks like so you don't let anything.
We just introduced the concept of margin, right? What is margin for a hyperplane? The margin is defined as the minimum distance between the data points and the hyperplane, right? So that means the margin is less than or equal to the distance between actual point data set and the hyperplane. Right? And what does the left-hand side of the input mean? Huh?
Just the distance.
Yes, it's distance, right? Look at this. You just replace w with u. Because u is unit vector, right? So we omit the denominator here, right? Because the norm of u is equal to 1, right? And because you correctly classify all the examples, so the numerator is just this product, right? So now you say here, yi times u transpose xi. Exactly the same thing, right? So left-hand side simply represents the distance between xi and u. So now, according to the definition of margin, we know gamma is actually a margin. In other words, gamma is the margin of the hyperplane determined by this unit vector u. That's the meaning of the second condition. And And then given the two conditions, we can claim that perceptron algorithm will always converge, and the number of total mistakes it will make is upper bounded by the largest radius, which contains all the training examples, over a margin of a separating hyperplane and t squared. That's the whole theorem, what the whole theorem tells us. Any questions? Okay. Yeah. I hope everybody should well understand this theory. What does the first condition mean? What does the second condition mean? And here, someone may ask why we require the existence of unit vector U, right? Why not we just require a free vector U which can perfectly separate the data, right? Of course, it is doable. Right? But if you use the arbitrary vector, classification vector U, right, and then your upper bound of the mistakes will be revised as this. That means the number of mistakes you made is R over gamma times the norm of U of t squared. So we will introduce the proof of this theorem, and later we can follow the same procedure to get this one. So basically, mystic bound theorem, although it is long, it just says, suppose we have a binary classification data set with n-dimensional inputs and is separable, then the perceptron algorithm will always converge and find a separating hyperplane after making a finite number of mistakes. Thus, the meaning the mystic bound theorem delivers. So now let us go to the proof. The proof is not that simple, but is not trivial, but it's not very hard. It just consists of 3 steps and using infinity tricks to get upper bound of the number of mistakes. So the setting of the proof is that we initial all weight vectors in 0, and we set learning rate to be 1. And the two conditions in this proof can be expressed by 2 inequalities. Right? The first inequality is that the norm of each training example is less than or equal to R. The second is that we always have yi times u transpose xi is no less than gamma. Keep this in mind. So now let us do the proof. So we'll first prove 2 claims, right? And the second, the first 2 steps. And the third step, we just combine the 2 claims together to get upper bound of the number of mistakes. So the first claim is that when running perceptron after t mistakes, we have an inner product between the u vector, which can correctly classify all the training examples, and the current weight vector wt is lower bounded by t multiplied with this margin gamma. So how can we prove that? We use induction. Induction assumes that, okay, at the step t, this inequality holds, right? And we'll check whether at step t plus 1, this inequality holds as well, right? So we can verify it. It's straightforward. So the inner product between u and wt plus 1, according to the updating rule, right? Wt plus 1 is wt plus yi xi, right? Is u transpose wt. We substitute this summation for wt plus 1 to get this. Right? And then, according to the second condition, we know that yi times u transpose xi is always no less than gamma, right? So now we get u transpose wt plus 1 is no less than u transpose wt plus gamma. So remember, we're doing induction, so assume in t step u transpose wt is no less than t gamma. So we immediately get u transpose wt plus 1 is no less than t plus 1 times gamma. Okay. And the second step is just to verify the initial condition, right? When w0 is 0, obviously you have u transpose w0 is no less than 0 times gamma, right? both sides are 0. So we'll finish the first step. So now let us look at the second step, right? The second step is to prove a claim that after t mistakes, the square norm of the current weight vector is upper bounded by t multiplied with r squared. And to prove this claim, we use induction. Again, we assume at step t this increased holds, and we'll look at t plus 1 whether this increased holds as well, right? To see this point, we just substitute that w t plus 1 with this updated rule, right? Which is wt plus yi xi, and take norm squared, right? So we just expand this square term. We get 3 terms. The first term is the square norm of wt itself. The second term is the square norm of yi xi. Remember, yi is all either 1 or minus 1, so when we take square, it's just 1, right? So we can throw out yi. So the second square term is just xi norm and take square. And there's a cross term, right? 2yi multiplying with the inner product of wt and xi. So now, what about this, the cross term, the cross production term? An idea? What? So remember, we're making a mistake, right? The perceptual algorithm will update only when making mistakes. That means when we make a mistake, that means the true label multiplying with the inner product is always negative, right? So it is upper bounded by 0 here, right? And for this, for the right hand, for the rightmost square term, according to our first condition, we know the square norm of xi is less than or equal to r squared, right? So now we can upper bound the right hand by wt squares now, wt's norm squared plus r squared. Now, because we're doing induction and we assume at t step it holds, that means the wt square, wt norm square is less than or equal to t r squared, right? Plus r squared, we have wt plus 1's square norm is less than or equal to t plus 1 r squared. So induction holds, right? And then we check the initial condition. Obviously, when w0 is 0, we have a 0 less than or equal to 0. Right? So using the induction again, we can prove the second claim. So I'll suggest you to review the proof step. It's pretty straightforward, right? You can just follow the proof. And finally, given the 2 claims, after t mistakes, so we have inner product is less than t gamma, and square norm of wt is upper bounded by tr squared. Right? We want to connect the 2 inequalities to upper bound t. How can we do that? We'll first start with the second inequality. We take the square root of both sides and then reverse the inequality. We got r square root of t is no less than the norm of wt, right? And the second, we use the very important inequality, it's called Cauchy-Strauss inequality. That is the norm of wt is no less than the inner product between the unit vector u and wt. Why? According to the definition, right? It's a definition from our geometry class. The inner product between u and wt is the norm of u times norm of wt times the cosine of the angle between the 2 vectors. This definition of cosine. And then, because u is unit vector, right? And cosine is always less than 1. So you immediately get this. This is also called Cauchy-Strauss inequality. And now with this, we can put the t gamma on the right hand side, right? So we can say the leftmost term comes from the second plane, and the rightmost term comes from the first plane, right? Now we just connect them together, we know that our square root t is no less than t gamma, and then we can immediately get t is less than or equal to r over gamma squared. That's how we finish the proof. So this is a very classical proof in learning theory. So everybody should know that. And consists 3 steps. The first and second steps are just proof to look seemingly like irrelevant inequalities. But in the third step, they use Cauchy-Schwarz inequality to connect them together, and then we get upper bound for the number of mistakes. That's how we get bound for the number of mistakes. Any questions so far?
Sorry, so is UT like a normalized ideal weight vector that gives you that marginal gamma for your system?
U is unit vector.
Changing U the whole time.
What?
You're not changing U the whole time. You're taking WT. U describes that hyperplane that you have.
Yeah.
That is the ideal marginal gamma.
It's not ideal one. It's as long as it is a separating hyperplane, that's enough.
So you can be in that.
You can be arbitrary vector which can perfectly separate the string data. That's it. Okay, I will. Let us discuss next Monday. I will give a geometry explanation of this from here. When we do the review.